Beauty that's skin deep. Sanitary napkins. Find out the secret to their absorbency. And concrete pipes. A report from the underground. The term robot comes from the Czech word robota, which means forced labor. Most robots are designed for repetitive work that's difficult, dangerous, or would just bore human beings to death. Robotic arms have varying degrees of freedom, meaning they can pivot in different ways. A robotic arm resembles a human arm. It has a shoulder, an elbow, a wrist, and a hand. The shoulder is actually a stationary base to which the rest is attached. An engineer first designs all the parts on a computer. Then, those plans go into action. To form the base's outer casing, they bend steel sheeting into shape using a computer-guided press. Next, they paint the casing in powder paint using an electrostatic process that guarantees a thorough, even coat. They run a negative electrical charge to the casing and a positive charge to the paint particles. This makes the casing draw the paint to it like a magnet. Once the paint on the base casing dries, they use silkscreen printing to apply what's called the user diagram. It illustrates which parts move where and how. Now they build the robotic arm's hand, called the end effector. Robots can be outfitted with all sorts of end effectors. Here they're making a gripper whose two claws come together to grasp and carry objects. To make each claw, an automated metal drill cuts a groove lengthwise and widthwise in a piece of aluminum. They assemble the electrical circuit board that will later go inside the base. The robotic arm's 6 separate motors will plug into it. Next, they assemble the mechanical parts of the base. First, the motor that makes the arm rotate. Then the gear that goes on the vertical shaft holding the robotic arm upright. When the motor makes the gear and the shaft turn, the robotic arm turns with it. At the arm's shoulder level, they install a system of 4 pulleys. Each consists of 2 plastic wheels on a separate axle with a rubber belt running between them like a clothesline. The belt has little teeth that grip grooves on the wheels. It rotates the wheels, making the robotic arm move. Each joint in the robotic arm is capable of and programmed for a specific range of movement. Like the human arm, the combination of these movements manipulates the end effector. They plug an electrical wire that links the gripper to the shoulder into a circuit board located in the shoulder. Then they screw the entire arm to the base. They link up the wires from the circuit board in the base to the motors in the shoulder. To do this, they have to bunch the wires, 48 of them in total, and thread them through the shaft that attaches the base to the arm. Once everything's connected, they fine-tune and test the gear and pulley systems to see if they run smoothly. Now they can install the gripper and the shaft and gear system that operates it. Turning the gear one way opens the grip, turning it the other way closes it. Now they mount the assembled gripper to the forearm, plugging its motor into a circuit board that they've already installed there. They plug the wires from all 6 motors into the main circuit board, which they then install at the back of the base. The robot controller, the brain that runs the arm, is a separate unit. It controls everything connected to the circuit. To move the robot, the computer inside the controller switches on all the necessary motors. It can control 8 motors, 6 in the robot and 2 optional accessories. You can program it to perform a variety of tasks. From start to finish, it's taken just under 30 hours to assemble this robotic arm. It can lift up to 4.5 kilograms, about the weight of a full-grown cat, and it can move at a speed of 2 kilometers per hour. Most robots are reprogrammable, meaning that to change their behavior, you simply write a new program. From an employer's perspective, robots may be the ideal workers. Granted, they have no ideas of their own, but their productivity is constant, they never call in sick, and they never take lunch or coffee breaks. Tattooing dates at least as far back as the Bronze Age. A 5,000-year-old body found in a European glacier had several tattoos on his skin. Archaeologists have even uncovered what they believe are Stone Age tattooing instruments, sharp bone needles and clay discs containing mineral pigments. Walk into a tattoo parlor and the vast selection of elaborate designs will astound you. Once you make your choice, the tattoo artist traces the image. Next, he places the traced image on carbon paper and retraces the lines. This creates a carbon outline of the tattoo on the reverse side. The artist will use this blueprint, as it's called, as his guide. He cleans the customer's skin, then firmly presses on the blueprint. The carbon image transfers easily because the skin is damp. Now it's time to construct the needles. Most tattoos require 2 needles, one to make the outline of the image, the other to shade and color it in. Each needle is made up of as many as 20 smaller needles. The artist aligns these small needles in a jig, then solders them together onto one end of a steel rod. There's an eye on the other end. The number of small needles in a needle depends on the tattoo design, how thick its lines are, how big its colored areas are. The finished needles go into an autoclave to be sterilized. That takes 20 minutes at precisely 170 degrees Celsius. The tattoo artist uses that time to assemble the tattoo gun. After cleaning the frame with rubbing alcohol, he installs the motor called the coil. When an electric current runs through the coil, it oscillates the needle at up to 50 times per second. Once the 2 needles are sterilized, he takes the one for outlining, called the liner, and slides it into the tattoo gun. He hooks the eye on the other end onto the spring. As the spring moves back and forth, it moves the needle up and down. The tattoo artist stops and starts it with a foot pedal, like a sewing machine. Time to tattoo. He turns on the power supply to 10 volts and dabs the needle in the ink cap. The gun sucks up the ink. Some petroleum jelly on the skin helps the needle glide more easily. He begins by tracing the lines of the blueprint. The needle punctures the skin at a rate of up to 3,000 times per minute, injecting microparticles of ink which intermingle with the cells of the dermis, the skin's second layer. The artist continually wipes away the excess ink to keep his work area clean. After finishing the outline, he reapplies petroleum jelly. This seals the pores of the skin and prevents bleeding. Then he changes to the other needle and begins shading and coloring the image with a back and forth movement. He applies one color at a time, overlapping them to ensure thorough and even coverage. The needle can penetrate from 1 to 4 millimeters, and a good tattoo artist knows just how deep to go to create the different parts of the image. For example, he has to inject the outline the deepest, but going too deep can tear the skin and cause excessive pain and bleeding. But not going deep enough misses the dermis and leaves marks after healing. The cells of the dermis are remarkably stable, so tattoos last a lifetime. This tattoo has taken approximately 45 minutes to do from start to finish. The area will dry and scab over. Then, the scab will fall off, and this body art will be ready for exhibition. Believe it or not, World War I led to the invention of disposable sanitary napkins. American nurses serving in France discovered that the bandages they used for the troops could double as very absorbent menstrual pads. This led the bandage company to introduce disposable sanitary napkins in 1921. Today's disposable sanitary pads are made of layers of cellulose combined with superabsorbent polymer powder. Polymer is a fluid-absorbing chemical derived from either petroleum or wheat. Cellulose is the fiber that makes up the cell wall of trees and plants. It also retains fluid. Pulp and paper companies grind and moisten it to form a product called pulp. Producing sanitary napkins begins with half-meter wide rolls of cellulose pulp. The rolls feed one long machine that does everything. First, knives spinning at 3,000 RPM shred the pulp into a fine fluff. Then the machine sprinkles that fluff with polymer powder. The polymered fluff then travels through what's called the doser, a device that measures out the required amount of fluff per pad layer. The machine then suctions each dose into a closed chamber, where an air current blows it into a pad-shaped mold. Then another air current blows it out of the mold onto a wheel that transfers it to a conveyor belt. The machine simultaneously makes a second pad layer. This one is smaller, rectangular, and at least double the density of the first layer, meaning it has more cellulose compressed into a smaller size. The compression roller also embosses a pattern that will disperse the menstrual flow, helping absorption. This demonstration shows the critical absorption role the polymer powder plays. It can retain up to 40 times its volume. As the polymer soaks up the liquid, it transforms from powder to gel. Different types of polymers have different reaction speeds. This type absorbs at average speed. This will be a 2-layer pad. The number of layers and their weight depends on the degree of menstrual flow a pad is designed to absorb. Now the machine's conveyor belts merge, bringing the 2 layers together. Now the machine sandwiches the layers between plastic sheets. The top one is perforated to allow fluid to pass to the absorbent layers underneath. The bottom one acts as a leak-proof barrier. A roller stamps the contour of the pad, sealing the absorbent layers inside. Now the machine applies glue to a paper strip and to a pair of small paper rectangles. It slaps the strip on the back of the pad and the rectangles on the side flaps, called the wings. To secure the pad to underwear, you remove the paper to expose the adhesive. The pads are still connected to each other. A cutting die excises each one. Abrasive foam on either side of the die grips, then pulls away the material surrounding the pads. A vacuum then sucks this excess away. Now the pads move onto the packaging line. The equipment first folds over the adhesive wings, then folds each pad in 3. The folded pads now go into plastic wrap. A hot iron-like device called an embossing press seals the plastic around each pad. Then a knife cuts in between the pads, separating them into individual pouches. Next, Two belts sandwich the pouches and carry them down to the stacker, where an automated counter lines them up for packaging. As a vacuum opens the bag, a mechanical arm inserts the pads. The equipment then seals the bag shut. Everything you've seen happens at an impressive pace. From start to finish, it takes just 40 seconds to make and package a sanitary napkin. Most underground sewer and drainage pipes are made of reinforced dry mix concrete. Reinforced refers to the fact the concrete has steel bars inside it for added structural strength. Dry mix refers to the type of concrete. You can mold it, then immediately extract it, and it holds its shape. Concrete pipes can be as small as 25 centimeters or as large as 3.5 meters. It has a 100-year lifespan. Dry mix concrete is made of stone, coarse sand, Portland cement, which is a finely ground blend of clay and limestone, water, and a chemical that acts as a water reducer. Trucks unload the sand and stone into outdoor storage bins. The materials automatically drop onto a conveyor belt, which transports them to storage silos above the factory floor. The cement arrives by cement tanker, which blows it into a silo. All the silos feed the mixer. As the ingredients blend, the cement and water combine to form a paste that coats the sand and stone. The water reducer enables them to use minimal water. The less water, the stronger and more durable the concrete. Meanwhile, workers use a special machine to build what's called the cage, a circular steel frame that will form the pipe's internal structure, its backbone. They insert 2.5-meter-long steel rods in a circular configuration, pushing each rod partway through the machine to the other side. There, an automated spot welder fuses a steel cable to one rod. Then the machine begins turning, winding the cable tightly around the rods. Here, a worker is turning the machine manually just to show us the process in slow motion. This is what it looks like at the normal automated speed. As the rods pass through the machine, the welder fuses the cable to them in one continuous spiral. As the spiraled cable reaches the end of the rods, the machine's claws spread outward, forming a wider section on the end. This is called the bell section. Workers position it on a base ring designed to hold the cage in place. Then they close a hinged steel mold over it. Now they're ready to pour the concrete. A forklift transports the mold to a machine called the packer head. They position the mold directly under it. A long drill-like screw descends into the mold. As concrete pours in, the screw turns at high speed, moving up and down. Its blades propel the concrete outward against the mold walls, forming the pipe. This process is called centrifugal projection forming. The process for making large diameter pipes is slightly different. A welder fuses spacers to the cage, both inside and out. These will center the cage inside the mold. Workers position the cage onto a base ring, then lower the outer part of the mold, called the outside form, over it. After securing it to the ring, they lower the unit over the smaller inner part of the mold, called the inside form. An overhead funnel pours concrete into the cavity between the two mold forms. Powerful electrical vibrators shake the mold. This forces the thick concrete downward, filling the cavity. This process is called vibration forming. With either pipe forming technique, the molded concrete is quite fragile, so the molds go off to the curing warehouse to harden. There, workers remove them, leaving the pipe standing upright. Steam hoses transform the curing warehouse into a sauna. The temperature rises to 60 degrees Celsius, the relative humidity 100%. The concrete hardens in about 12 hours. Concrete pipes buried underground have to be able to withstand the weight of the earth above them, so the company subjects sample pipes to extreme pressure to test their maximum resistance. Concrete pipes join together with watertight rubber gaskets. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.